class. This is where we left off last time. We had this problem, and we had the differential equation right here, and we separated the variables and the integral right here in this step, and we got the natural log of y. And so in order to solve for y, we raised the exponent to e so we can cancel out the natural log, and we got ce raised to the kth power. And then from there we used our initial value of 100 gallons at time 0 right here to solve for the big constant. And so that took us over here to this part, and we had to solve for k. So we used the second condition, 10 hours and 70 gallons, and came up with k value equal to natural log of 7 over 10 divided by 10. So we took care of part A. So from here we're going to take a look at part B, and we're going to see how much water would have leaked out after 5 hours. Well, since we just found the amount of water left, that's important. That's the amount of water left after so many hours. So, and just remembering that we started out with 100 gallons up here, so maybe we could have drawn a little picture up here where we had some water that was so high and equal to 100 gallons. So let's take a look at the calculator and see if we can get this plugged in there relatively quick. And we have the fact that we can put this in the calculator in this part right here, and we have y is equal to 100, and we're going to take e and raise it to the, now remember we just found k. This is going to get a little bit tricky here. We have, maybe we should put parentheses around the numerator, which is the natural log of 7/10. So we have the natural log of 0.7, like a type, at 0.7, close that parenthesis, and divide by 10. Now we'll close that parenthesis. So I started off with the parentheses for the numerator, so parentheses right here. Okay. Then we have, actually, explain what I'm doing in a second. Okay, this last outside parentheses is actually covering up, or it's closing out the exponent e raised to the exponent value. So right in here I'm going to insert the x for our time, really t. Okay, well they want to know when time is equal to 10, what is this equal to? So let's go to our table, and at 5 the answer is 83.666. So that's how many gallons are left. So y at 5 is equal to 83.666. I bet it rounds up to 67. So we started off with 100. 100 minus 83.667 is going to give us our correct answer of 16.33 gallons. So that's how much water is leaked out. 16.33 gallons. Okay. So set up the integral. Solve for 83.667. You probably get a point for doing that properly. But to get full points, you'd have to recognize that y is the amount of water left. Okay, so that's the C curve. All right, so let's move on to part C. it says, so what is the average value after during the first 20 hours? So during the first 20 hours, we have the fact that I want to know how I'm recording. Hang on a second. All right, so after that interruption, sorry about that. So part C, they want to know the average amount of water in the reservoir during the first 20 hours. Well, we know that Y is equal to the amount of water left, so we're just going to take the average value from 0 to 20. So we're going to use our formula. Multiply it by the integral from 0 to 20, and we are just going to call this y of t dt. All right, well, since we already have this in the calculator, we're going to let the calculator do all the work for us. So double check, make sure we have it in there. So let's quit out of this, and we're going to take 1/20th times that integral. So we're going to let the calculator do it for us. Go down function integrator, and y1, your variables, y1, using x as the variable, and the lower limit of integration is 0 and the upper limit is 20. So we get this 71.494 is the average amount of water in the reservoir in the first 20 hours. So it kind of makes a little sense. So we're going to put down 0.494. All right, so make sure you get the units right. Since we're talking about the amount of water, it's going to be in gallons. All right. I haven't been doing a very good job of this, but make sure you put your answers in a box. All right, let's see. Part D says, after how many hours of leaking will the amount part C be in the reservoir? So when is this equation going to equal 71.494? Let's see if we can get a little more paper here. So let's write down our equation. If 71.494 is equal to 100 e to the kt, so k is natural log of 0.7 divided by 10, and oops, we forgot to put our variable in here, so let's put t in. So times t, and we need to solve for time in hours. So first thing we could do is divide by 100, and then we're left with this e. Well, how do we get to this t that's buried inside of this crazy function? Well, we're simply going to take the natural log of both sides. If we take the natural log of both sides, we're going to get that we have the natural log of 0.7 divided by 10 times t. So natural log of 71.494 over 100. Well, instead of writing that, we could just move the decimal over twice. Write 0.7149. Let's see if we can do this with a calculator now. And then we're going to divide by the natural log of 7 over 10. Or excuse me, 0.7 divided by 10. Okay, be careful right here. Don't do what I just did. This is the natural log of 0.7 on top. All of this divided by 10. Very careful right there. Okay, so let's come over here and see what we can do with this one. we have a natural log of 0.71 divided by 100. Okay. And then we're going to multiply it by 10. And then we're going to take that and divide it by the natural log of 0.7. And we made a mistake somewhere. I divided it by 100 a second time here. Let me go back. Large move the decimal twice right here. That's where we made our mistake. Okay, so we have the natural log of 0.71 times 10. Now we're going to multiply or divide that by natural log of 0.7. So, okay, we get 9.6. 9.60. 9.602. All right. Well, on a problem like this, I would probably go through the table and go down to 9 and see if that doesn't get approximately close to 71.494 gallons, and it does. So it should be okay on this one. Okay, let's take a look at the next section. I'll go ahead and pause the video here and stop it, and we'll take it up